We now come to the case of one-dimensional motion with varying acceleration. Now, in the first case, we are taking where acceleration is given to us as a function of time. Say for example, here it is given 3 minus 2t meter per second square, where t is in seconds. And also it is given that at t equal to 0 or at the initial moment, the velocity is 2 meter per second. We have to find the velocity at t equal to 4 seconds and also what will be the displacement at the same moment t equal to 4 seconds. So how to do this? See, if acceleration is given to us as a function of time, what we can do is we can write acceleration as dv by dt. So this is 3 minus 2t, and then we can integrate this. dv integral will be 3 minus 2t dt integral. Limits for time 0 to, let us say t. We have to find velocity at 4 seconds, but let's solve this for a general time t so that we can find velocity as a function of time. Now at t equal to 0, the velocity is given to us as 2. So here it will be 2 to some velocity v at time t. Left hand side, integral is simply v, integral of dv is v, 2 to v. Right hand side it is 3 becomes 3t minus 2t is your t squared, and the limit 0 to t. So we get v minus 2 is equal to 3t minus t square. Or the expression for velocity we are getting as 3t minus t square plus 2. So using this we can easily find the velocity required at 4 seconds. Just put the value t equal to 4. So you get 12 minus 16 plus 2. So this is 14 minus 16 minus 2 meter per second. So that is the velocity. Minus means it must be moving in the opposite direction as compared to its initial velocity. If the initial velocity was towards right, the final velocity is towards left. Now how to find displacement? We will have to integrate it once again. We will have to integrate this expression of velocity, general expression of velocity as a function of time. We can integrate this to get s. We can write v as ds by dt. So ds by dt is equal to 3t minus t square plus 2, that and we can integrate this to get, now integral of ds, let me write it clearly, ds integral integral of 3t minus t square plus 2 dt, limits for time 0 to, now we can put it 4 because our aim is to find displacement at 4, and this is 0 to s. So this becomes s equal to, now I am taking initial displacement has to be 0 because for displacement you need some time. Displacement is being measured from the starting location, so it is 0 initially. Here it will be 3t integral gives you 3t square by 2 minus this will be t cube by 3 and plus 2t, and the limits are 0 to 4, and you can do the final calculation. Becomes 3 times 16 by 2 is 8 minus 4 cube is 64 by 3 and plus 8. So this can be simplified to, this will be 32 minus 64 by 3 becomes 96. If you take the LCM, 96 minus 64 is your 32 by 3 meter. So this is the final displacement in 4 seconds. We can do one thing here. This looks very much mathematical, all the way equations. We can do something here for visualization. The advantage that we have is that acceleration is a linear function of time. So we can get the velocity at least with the help of graph. Which graph? We will draw acceleration time graph. So acceleration time graph will be a straight line, positive intercept, negative slope. So the acceleration time graph will look something like this. Initial acceleration is 3. Acceleration becomes 0 at this point at 3 by 2. So 1.5 seconds acceleration is 0. We have to find velocity at 4 seconds. So 4 will be somewhere here. Now area under the acceleration time graph, what does it tell us? It gives us change in velocity, right? Integral of a dt will give you change in velocity, final velocity minus initial velocity. Alright, that's what this integral is giving you. This is change in velocity and this is area under AT graph basically. So now this is positive above the axis. How much? This is half 3 multiplied by 1.5. And we have to subtract this area. This is 4 seconds, so this is 2.5. So half multiplied by base is 2.5 multiplied by height. What will be the acceleration at t equal to 4? You can put t equal to 4 in this expression. So you are getting minus 5. Acceleration here is minus 5. So the height of this triangle here is 5. So you can see the change in velocity we were calculating by like finding the area under graph. It becomes half multiplied by 4.5 minus 7.5. So change in velocity is negative 3 by this is 12.5 actually. So this is 12.5. So this is 8 by 2, negative 8 by 2. So this is minus 4 meter per second. That is the change in velocity during the first 4 seconds. We can find this using graph here. So what will be the final velocity? See, change in velocity, the initial velocity was given as 2. So you can see the final velocity will be 2 and add the change to it. The change is minus 4. It becomes minus 2 meter per second. So it is the same answer which we got using our method of integration and equations. We could have got this from graph also, but this will work provided acceleration is a linear function of time. Only in such a case you can find area under the graph by ordinary calculation. If the graph is a curvilinear, the only way that we have is to integrate. So here, in order to find the displacement, you don't have any option. You have to integrate this because the velocity is becoming a quadratic function of time. So by integration, we could find the value of displacement. The second case of acceleration of 1D motion with the varying acceleration. Here acceleration is given as a function of x. If acceleration is given as a function of x and we write acceleration as dv by dt, there will be a trouble. Because if acceleration is a function of x, here we have 3 variables v, t and x. the problem will become solvable if we can reduce it to two variables, and that can be done with the help of chain rule. On the left hand side, if we apply chain rule, we can write the acceleration as dv by dx times dx by dt. Dx by dt we know is v, so acceleration becomes v dv by dx. Now, if acceleration is given as a function of x, we can take dx on the other side and integrate it. So, integral of v dv becomes integral of a dx. And let us say the position changes from x1 to x2 and the velocity correspondingly changes from u to v. So, this is basically area under the graph. Suppose in a situation you have acceleration versus position graph, maybe something like this, then the left hand side, what it represents is this area between two vertical lines x1 and x2. So this area, what is it equal to? If you look at left hand side, this we can integrate. Integral of v is your v square by 2 within the limits u to v. So it can finally be written as v square minus u square by 2, and this is equal to this area a dx integral from x1 to x2. So the area under acceleration position graph gives you v square minus u square by 2. So knowing the value of u, we can find v using this relationship. In the third case of motion with varying acceleration, we may be given acceleration as a function of velocity. Let's understand this case with the help of one example in which a motorboat which was moving with a velocity v0, its engine is stopped at the moment t equal to 0, and once the engine is stopped, it begins to retard due to, you can say, water resistance. The acceleration after it has stopped is given by minus cv, negative, so that its velocity is decreasing. Now in this situation we have to find velocity of the motorboat as a function of time, velocity, also its velocity as a function of its displacement x from this moment when the engine is stopped, and the total displacement till it stops. So for the first part, we will write acceleration as dv by dt, because we are interested in getting the relation of velocity with time. So we will write a as dv by dt. So dv by dt is equal to minus cv. We can separate the variables, becomes dv by v is equal to minus c dt. At t equal to 0, velocity was v0, and at some general time, let us say the velocity is v. Left hand side on integration is log v, limits are from v0 to v. Right hand side is simply minus ct. This becomes log of v divided by v0, log v minus log v0, you can write it as log v upon v0 minus ct. And finally, if you take the log on the other side, this can be written as v by v0 equal to e to the power minus ct, or v is equal to v0 e to the power minus ct. So this is the required expression for velocity as a function of time. Now for the part 2, where we have to find velocity as a function of x, we can write acceleration as v dv by dx. When acceleration is given as a function of velocity, we have both these options. We can write velocity as a function of time as dv by dt. We can write acceleration as dv by dt, or we can write acceleration as v dv by dx, because there will be just two variables in both these cases. So for this one, I am writing A as v dv by dx. So v dv by dx is equal to negative cv. Again, we will separate the variables. In fact, v is getting cancelled. So we just have a dv on this side. On the other side, it is minus c dx. X equal to 0, the velocity is v naught. At a general x, let us say it becomes v. So we can, the left hand side, very simple, is v minus v naught. The right hand side, after minus c, it is x minus 0. So you get v as v naught minus cx. So this is the answer to the second part, velocity as a function of x. Now the final part, we have to find displacement till it stops. Displacement till it stops. So that we can get very easily just by putting v equal to 0 here, because till it stops means v equal to 0. So for third part, I am putting v equal to 0 here. So 0 is equal to v naught minus c x naught. Let us say this x naught is the final displacement, gives me x naught is equal to v naught divided by c as the total displacement of this motorboat till it finally comes to rest. So this distance till it comes to rest is v naught by c. So this is how we can tackle the problems where acceleration is given as a function of velocity. We have both the options. We can either write A as dv by dt if we are interested in velocity as a function of time. If we are interested in the relation of velocity with displacement, we can write acceleration as v dv by dx also. Let's take a look at this example. We are given a graph of a body moving along x-axis. It is v versus x graph, and the graph is a straight line as shown. We have to find two things: acceleration at x equal to 2 meters and the time taken to go from 0 to 2 meters. Now, acceleration is looking at this graph, you may feel that body is moving with constant acceleration and the slope of the graph will be acceleration. But wait, be careful. Whenever you look at a graph, first you should look at what are the quantities on the y-axis and on the x-axis. On the y-axis we have velocity, all right, but on the x-axis it is not time, it is position. So slope of the graph will not give you acceleration. In a VT graph, the slope gives you acceleration. So the graph is basically giving us a relation between velocity and position. It's a straight line graph. We can very easily write this relation. Y is equal to mx plus c. What is the slope of this line? You can easily see that the slope of this line is what? It is 1, because delta v is 2 and the corresponding delta x is also 2. So if position changes by 2 meters, correspondingly velocity changes by 2 meters per second. So that gives you slope of 1. So it is 1 times x plus, and c is your y-intercept, which is, you can see as 2. So v is equal to x plus 2. This is the equation of this line or the velocity position relation. Now if v is given as a function of position, how to find acceleration? You can use the relation for acceleration in terms of v and x, and that is your v dv by dx. you must be familiar with it by now. Using chain rule, we get this relation. So we had to find acceleration at 2 meters. So what we have to do is we have to put the value of v and dv by dx at 2 meters. Now dv by dx is a constant. You can differentiate this to get dv by dx. In fact, dv by dx is 1. It is basically slope of this line. And the value of v at x equal to 2, value of v is 4. So acceleration at x equal to 2 will be 4 multiplied by 1, means 4 meter per second square. So we have done the first part, and clearly acceleration is not constant. Of the two factors, only dv by dx is constant. V is increasing. So as the particle moves towards higher values of x towards the right, its acceleration actually keeps on increasing. So it is not a case of constant acceleration. Now to the second part, we have to find the time taken by the particle to go from 0 to 2. We have already got the relation of v in terms of x. We can use this to get time. We can write v as dx by dt. So dx by dt is x plus 2. In this one, I have just written v, I have just replaced v by dx by dt. I can separate the variables dx upon x plus 2 equal to dt and do the integral. What are the limits for x given in the question? 0 to 2. And I have to find the time for this duration. So 0 to t. T is the unknown that we have to find. Left hand side, the integral is very simple. You can easily see this is log of x plus 2. And the limits 0 to 2 is equal to, right hand side is simply t. So we get t is equal to, if you put 2, it becomes log 4. And if you put 0, it becomes log 2. So log 4 minus log 2. Log 4 is 2 log 2. So ultimately this is log 2. This is the value of t, and you know that this is about 0.693 seconds. So that is the value of time. In this example, we are given a graph of reciprocal of velocity with position. Reciprocal of velocity is sometimes measured by these fitness trackers in terms of pace. They give it in terms of minutes per kilometer. Person is running and it gives minutes per kilometer. Here it is in SI units in terms of seconds per meter. And the position is of course in terms of meters. We have to find the time taken by the particle to go from x equal to 10 to 20 meters. Now it's a new situation for you because it's on the y-axis we are having reciprocal of velocity. So reciprocal of velocity is there, x is there, we have to get time. What is the relation that connects velocity position with time? The most obvious choice is v is equal to dx by dt. But in this example, what we are having is reciprocal of velocity. So I will take v on the other side, and on the other side, on the right hand side, we will have 1 upon v, and let's take t on the other side. So this relation becomes dt is equal to 1 upon v dx. Now, this is the relation that we are looking for, that we want to get time in terms of reciprocal of velocity and x. So if I just integrate this, I will get the required time. Integral of 1 upon v dx gives me the time duration. Now what is this? This is basically area under the graph. Integral y dx. On the y-axis, I have reciprocal of velocity. So I can get the required time just by calculating area under the graph. I don't have to actually perform the integral in this case because the graph is a straight line and I can very easily get the area. So the required answer for time, we can get it from graph, the area of trapezium, half of 0.2 plus 0.3 multiplied by the width, which is 10. So it gives us, this will be 0.25 into 10, or you can say 2.5 seconds. So this is the required answer for time taken to go from 10 to 20 meters.